Good morning. Great to see so many familiar faces here. Welcome back here. And I guess there are some of you who've not been to the Simons Institute before, so I should say a little bit about it. The Simons Institute is, it's now pretty well known in TCS circles for convening meetings like this and longer meetings about it's the premier institution in the theory of computing, but also with this view of the computational lens. So it has this really broad overarching view of computation and the sciences, collaborations between them, interdisciplinary. So one of the things that we host here at the Simons Institute is a quantum research pod, which has postdocs, senior visitors, programs. Students visit here. We organize the quantum Simons Quantum Colloquium, this is another event that's organized through the Quantum Research Pod. Lynn had a great idea about, he proposed this workshop, which is extremely topical. I think it's a really great idea, and he's been very much leading the charge on putting this together. I should say that I think this is a very exciting topic. We are all really looking forward to seeing what comes of this particular thing. And finally, let me, maybe I'll turn it over to Lynn to describe one.
Okay, thank you very much. Again, thank you for coming. My name is Lynn from the Math Department here. And Umesh said I came up with the idea to take the credit. Organized with Jim Lu from Duke and Lexing In from Stanford. We had some community meetings this morning, we'll join later. And also from CS, Min Liu from Harvard, and also Ewan Kang from here, who's a middle fellow. So it's a very interdisciplinary program on this open quantum systems. We very much would like to thank the Simons Institute, the Quantum Pod, and Umesh for supporting this, because we came up with this idea, want to have this meeting within 3 months notice or something. It's very hard to do, and we really greatly appreciate the opportunity. So the purpose of this is really to talk about open quantum system problems. As many of you know, the theory got a lot of development in the 70s and 80s, and then died down a bit and became rather quiet for a couple of decades. And then there's a revival of interest, and which is pretty much now. And there are a lot of reasons for that, and as we'll hear pretty much starting this morning. So it's really aiming at bringing different perspectives, math and CS and physics and chemistry together. Also between classical and quantum. That's also very important, as we suggested, and we'll hear from the classical side as well during the week. Also, we hope this can be an opportunity for people from different communities to know each other, and also talk about important problems, open questions that are worth solving, say in the next 2 years. And for this purpose, we're going to start with unusual format, which means that the open question session will start this afternoon, even though we haven't introduced all the necessary things, but maybe give us some motivation. That being said, I have received 4 slides, 2 slides each for each talk, so 8 slides in total. That's a good number, but if you have some ideas and want to put up something, and please send it to me by lunch, and or even just a very brief sketch, and we can select it after that. And also after the slides, we will be open floor discussion. Should I also say that lunch and dinner on your own, and the closest one where the faculty club can pass around all the office in Southgate. And there will be a group photo this afternoon, right after the open problem session. Am I missing? Without further ado, let's welcome the first speaker, Senator Irani, who has very kindly to agree to give a friendly introduction to quantum Gibbs sampling and about its algorithmic ingredients.
Okay. I think I'm on, so I don't need that.
Okay.
All right. It's good to be back here, and I'm going to present some of the material that was helpful to me in starting to understand some of these newer algorithms in quantum Gibbs sampling. I hope by the end of the talk to be able to step through an algorithm from end to end. There will be almost nothing about proofs here, so my idea is just to give an idea of the algorithmic pieces and give some intuition about why they work. Okay. So let's start with the classical setup. Suppose we have some classical local Hamiltonian, think Ising model, something like that. The eigenstates are just classical strings. And our goal is to sample from the so-called Gibbs distribution for some fixed beta, where the probability of sampling a particular state x is proportional, inversely proportional to exponential in the energy. So we classically often achieve this by a discrete-time Markov chain, where we're walking along on the states of the system. And our Markov chain is described by a stochastic transition matrix. Given I'm at state I at time t minus 1, it's well defined the probability that I transition to j. So this is probably familiar territory for many folks. One of the kind of workhorses of scientific computing has been, over the last decade, has been the classical Metropolis algorithm, which converges to this Gibbs state. So you have some set of jump operators. Think in terms of the Ising model, flipping a random bit. It twiddles with your current state in some way. And then you decide, you make a decision. So you're starting at state x. There I am. And you pick a random jump operator, you apply it, you get some new state, and you think about accepting this move or not. And you accept the move with probability specified here. So if it's to a higher energy state, it's inversely exponential in the difference between the two energies. So to compute this probability, I always need the difference of the two energies. And then if we reject, we just stay at x. Okay? And so this, we know that this, here's the, and I will denote this, what did I do? I will denote this probability with this gamma throughout. Sometimes I'll drop the beta, sometimes I'll drop the difference, but hopefully it'll be clear from context. And our beta is typically polynomial, bounded by polynomial. So beta is the inverse temperature. So the temperature doesn't get too low, it's always at least 1 over polynomial. Okay. So we know that the Gibbs distribution is a fixed point of this process because it obeys a property called detailed balance, that probably transitioning in one direction when you're in Gibbs is the same as traveling back. There will be a quantum analog of this. I will say almost nothing about it during this talk because we're going to just take it on faith that the goal is to sort of simulate this type of process in a quantum setting. And then Andras, I think, will pick up and talk about detailed balance a little bit more carefully when you talk about actual proofs of convergence. So you need that the jump operators mix things up enough so that you can get from one state to another. Okay. So the goal here is to do this in a quantum setting. So we have a quantum Hamiltonian with eigenstates and eigenvalues, and we want to prepare the same distribution over these eigenstates. And a distribution over quantum states is usually represented by a density matrix in this form. So if I'm in a d-dimensional space, it's a d by d matrix. And this is sort of a shorthand. So the goal is to prepare this particular mixed state and to come up with some process that converges to this mixed state. Now, before we get to quantum, and challenges in sort of implementing just the standard classical Metropolis on a quantum computer are twofold. One is that we can't calculate energies exactly. So in the Ising model, it's trivial to determine what the energy of a particular state is. But in the quantum setting, we can only approximate that. And I will say more about that in a bit later on in the talk. And the second part is, if you really want to sort of mimic this rejection procedure, that's problematic, because deciding whether to accept or reject requires a quantum measurement, and then you have to back up after a quantum measurement. So before getting to the quantum, it was helpful for me to sort of understand a little bit more about continuous time classical walks, because some of the mechanisms are very similar. So I'm going to sort of do a brief overview of the mechanisms of specifying continuous time classical walks before I get to the quantum. So in continuous time Markov chains, the state varies continuously over time. You can hop at any particular time, as opposed to these discrete time steps. And the thing that makes it Markovian is if I'm the probability of transitioning from I at time s to j at time t plus s is independent of anything that comes before, or this should say s, anything that comes before s. So I just need to know where I am to know about my probabilities for the future. We will also assume time homogeneity, meaning that the probability of moving from I to j over an interval of length t is independent of when that interval starts. Okay, so the dynamics of the system aren't changing over time. So that allows me to specify for any particular time, I can specify a stochastic matrix that says this is the likelihood of going from I to j over an interval that lasts duration t. And it doesn't matter when the interval starts. Okay? So one way for me to tell you about the continuous time Markov chain is to tell you about the stochastic matrix about every possible point in time. Okay? So that would be, but that's really overkill. You don't need to actually specify everything about these functions. Because of the Markovian nature of the process, we can specify the walk by a generator matrix, which is essentially the derivative of this function of t. Okay, so this is the definition of the generator matrix. And let's talk about a few properties that it has. So the off diagonals are non-negative, and the diagonal entries are negative, and by definition here the rows sum to 0. And you want to think of an off diagonal entry, Pij. It's the flow of mass from I to j per unit of mass that's already sitting at I. So that's it's sort of the derivative of that as a function of the mass that you have already sitting at node I. So let's say a little bit of more, given that we've defined the generator matrix in this way, it satisfies the following differential equation. So this is the derivative of a particular distribution. The rate at which it's changing is a function, this product, the distribution where you are times this matrix Q. So this is telling us sort of the rate of change given a particular distribution. Okay, good. And given Q, then I can sort of compute the dynamics as I like. I can get back all of these probabilities, these transition probabilities, by solving that differential equation and taking the exponent. So, and we can get this exponent by using the Taylor expansion. Okay? So given Q, this is now a sort of a finite description of the process. I can sort of derive the transition probabilities for any particular time. And since Q is the derivative of the motion, if I have a fixed point, that should mean that I get 0 when I apply Q to it. So the derivative should be 0 and I shouldn't move. All right? So far, so good. And I found these lecture notes useful. If you want to look them up, I quote my sources. So I was digging around, and lecture notes by Miranda Holmes-Sirfan were helpful to me in understanding this material. So, and just to belabor the point just a little bit further, here's my Q. Once I specify the off-diagonal elements, the rest of the matrix is fixed because this diagonal entry has to be the negative of the sum of everything in the row. And that is necessary because any distribution, when I think about the derivative of that distribution, if I'm summing up over all of the probabilities, that derivative has to be 0, meaning that a probability distribution transitions to a probability distribution, and the sum is always 1. So if I'm summing up over all of the states, and I take the derivative, that has to sum to 0, because the mass of the probability distribution always sums to 1. And that's just saying for any probability distribution, this thing has to be 0. So by definition, this gives me that the rows sum to 0. So once we've determined those off-diagonal elements, the diagonal is completely fixed. Okay, and the reason I'm sort of being a little pedantic about this is that we'll see the analog in the quantum setting when we get there. Okay. So here's a generator for a classical continuous Markov Metropolis. I have some non-negative matrices. They don't have to be stochastic or anything. I do need that in distribution they're symmetric. But now I can define a continuous time metropolis, and here's the generator for it. I have the probability of going from state I to state j is I'm applying a jump operator chosen according to my distribution, and I accept with this probability. So this is the rate of flow from I to j. And then I just need to make sure that those diagonal entries are what they're supposed to be. So for the diagonal entries, I just subtract off everything I have in the row. And that guarantees me that likelihood. And so any such matrix will give a valid Metropolis-like algorithm. So of course, some jump operators are better than others, but this is sort of how you would translate that into the continuous setting. Are we good? All right.
Sorry, the symmetric condition is again some sort of...
I'm not 100% sure, but when I worked it out to get the detailed balance, I needed this to be true. Yeah, so in order to get the detailed balance, I think those have to be right. So, yes, Andras.
This is the original form of the Metropolis algorithm, and for non-symmetric, Hastings actually did. And the Metropolis Hastings algorithm is when you can also start with non-symmetric, but then you have to modify the data.
So these A's can be non-symmetric?
Yeah, and that is the generalization by Hastings, and that's why this is often called Metropolis Hastings algorithm, because the more general one was devised by him. But then the rule is something different to make sure.
To make sure that you get the detailed balance. Okay, cool. I was going to say at the beginning, it's likely I'm going to say something wrong, so it's really good that the experts are here to keep me honest. So thank you. All right.
So in order to do that, you do need to access the inverse.
Yeah.
Okay, and we have this. All right. So this format looks a little familiar to those of us who work in quantum, because if I just look at the evolution of a closed quantum system, I can specify that using the Hamiltonian H. And Schrodinger's equation says that the evolution of the dynamics of a closed quantum system is governed by this equation, which tells us then that the evolution of the system is unitary, and the unitary as a function of time is given here as an exponential of the Hamiltonian. And of course, there's been tremendous work over the last many decades taking this general formulation and then coming up with a quantum circuit that actually achieves and executes this on a quantum computer. So we'll see the analog in the open quantum system case. And so what we're going to do, and so just there's an analog here in that I have a fixed, it's almost serving the same function as the generator. I have a fixed description of the dynamics. It satisfies this differential equation. And then using that, I can sort of simulate the dynamics over any time period. Okay? And so we're going to generalize this now from the classical continuous to quantum. But it's also a generalization from closed quantum systems to open quantum systems. And we'll head to the Lindbladian formulation then. So if I have, if I start with a closed quantum system, I have a pure state whose L2 norm is 1. But I can trace out, if I'm interested really in some little patch of this, and I just trace out everything besides what I'm interested in, because there can be entanglement across this divide between my little system and the larger system, what I get is an ensemble of states, a probability distribution, which we generally present in this sort of density matrix format. This matrix format is very useful because then we can just operate directly on it. Okay, so this is a density matrix. It generally represents a state of an open quantum system, meaning that my system can be entangled with stuff on the outside. And it's a positive operator of trace 1. So I didn't know how much to cover, how broad the audience would be. So you can rephrase all of the postulates of quantum mechanics in terms of mixed states, these probability distributions, instead of on sort of pure states, unitary evolution. We can re-express Schrödinger's equation by applying the derivative to this and using the product rule. You get this formulation when this happens. And so this equation here is a reformulation of Schrödinger's equation, just using the language of mixed states instead of pure states. And this will come up because there will, in the processes that we'll look at, there will be a coherent part that's sort of evolving according to a unitary that represents just the operations inside the system, and an incoherent part where the evolution is not unitary. We'll be talking about linear operations on these mixed states, and if it's useful, you can think of representing these things not as d by d matrices, but as a sort of, you can string them out as a d squared length vector. And then the notion of inner product here corresponds to sort of the natural notion that we have in the vector space. So here, the inner product of two density matrices is given by the trace of this product. And in those cases, and in this formulation, then any linear operation on a density matrix really can be represented in its matrix form. So, but most of the time, we'll stick to the matrix representation. Okay, so here we have a situation, and we want to generalize our picture of evolution of a system. So I have some larger system, and it's evolving over time. Okay, at time 0, I can trace out, and I'll get some mixed state. Then I let it evolve for a bit, and then some later t I trace out, and I get some other state. And what I'd like is a description of this process, just on the smaller system. What are the dynamics on that smaller system? And is it possible, so first of all, we know by virtue of the fact that this process came about by evolving on a larger system, we know something about this mapping. We know it's completely positive and trace preserving, just by virtue of the fact that it was kind of created in this way. But you could ask, is there some kind of linear map that describes the dynamics here that's independent of all the degrees of the bigger system? So can I do sort of a similar thing that I did with the Hamiltonian picture, but now just describing now a process that transfers mixed states to mixed states? And the answer is not always, as you could imagine. So you could imagine that the dynamics of the system over time, as it evolves over a long period of time, it really does depend on the degrees of freedom in this big, larger system. So, but in certain cases you can. And there's sort of a more physicsy derivation of the Lindblad master equation that uses this. So under some assumptions, in particular that the interaction terms between the smaller system and the outside are weak enough, you can actually, it is true that you can describe the dynamics independent of the larger system. And in that case, this L takes on a particular form. There's also an alternative derivation of the Lindblad equation, which I'm going to sort of sketch or talk a little bit about, which simply asks, sort of from a mathematical perspective, what's the most general form for a linear map, L, that would satisfy this equation, which would guarantee me that then the resulting dynamics is always CPTP. So how general, what does this look like in order to guarantee that if I solve this equation and I look at sort of the resulting dynamics, this map from density matrices to density matrices always has a CPTP form. Okay? I'm going to sketch the derivation of the Lindblad equation. If I'm incoherent for the next few minutes, there will be a jumping in point. So I want to just give a little bit idea, because I think the derivation gives some intuition about the different terms in that Lindbladian, which I think will be helpful to have. Okay? At the end, we'll end up at the Lindbladian, and then we can take off. So if I'm incoherent, there will be a jumping in point. So what do we know? V, the resulting V is a linear map. If it's completely positive, then it can be expressed in this way. This is not the definition of completely positive you would get from Wikipedia in the first paragraph, but it's an equivalent definition, so this is the one I'm going to use here. And then if it's trace preserving also, then we can add in this constraint. So we have these two mathematical constraints on what we get from V. Okay? Okay, so what are we going to do? We're going to compute this derivative. This is exactly the same way that we did the derivative in the classical continuous case. And we know that this mapping here is completely positive. So I can express it in this way. All right? So instead of using these operators, which are particular to V, I'm going to express this completely positive map using a generic basis. Okay? It's a D by D matrix, and here's my matrix, and it's orthonormal. Okay? And I'm going to make the decision that the first operator is going to be the identity. Okay? So when I make that decision, then the trace of all the other operators has to be 0. Okay? And the reason we might want to organize it this way is that, think Metropolis. Metropolis, you have these operators that take you to some other state. The accept operator is one where you tweak the state a little bit, you think about moving, and you accept it and you go, versus staying place, which is kind of the identity. So we have like these operators that have trace 0. That kind of represents moving somewhere else. We have off-diagonal entries, and we're moving somewhere else. And we have this alternative where we just stay in place. And that will help us sort of organize the terms accordingly. Okay, so we know that V can be expressed somehow in this basis. We do a bunch of fiddling around. There's about a page of derivations here. These G's incorporate taking the limit over delta T. At the end of the day, I can express this thing in this sum, and I've organized the terms in 4 groups. These are all the trace 0 terms. This has the identity on the right, this has the identity on the left, and this has the identity in both places. Okay? And the reason that we're going to do this is that this kind of is the form that we get the Lindbladian in. This is trace 0. So this, when we get this, when we mess around with this term a little bit, this is going to be sort of representing moving away, the accept operator in which we transition. And this will be necessary to sort of maintain, and so this will be kind of representing the rejection option where we stay put. Okay? But right now it's just, you just kind of plug this in and collect your terms, and you get some linear combination of these things. And this can be expressed, simplified in this way. Okay? There's the simplification. Now for G, I can separate it out into anti-Hermitian and Hermitian terms. And that gives me already the coherent dynamics when I take the Hermitian part.
Okay. G rho plus rho G dagger.
Wait, this here? Yeah, so to get these two, it's either G plus G dagger or G plus.
On the screen, G rho plus rho G.
Oh, yeah, so I forgot a dagger in there. Thank you. Yeah, and I should have had them throughout, so. Okay, so now we only had used the completely positive assumption, and now I'm going to throw in trace 0, okay? Trace 1. And this is analogous to what we did in the classical case where, remember, the rho had to sum to 0 in order for the mass to stay, the total probability mass to stay constant. Here, if it's a trace preserving, that means the trace of the derivative or the derivative of the trace has to be 0. And given that that's the case, there's only one form that this f can take. It essentially has to be the same as this. When we apply the trace, we can use the circular nature of the trace, and essentially it means that there's only one form that f can be. And then we diagonalize and we get the Lindbladian equation. And I think I have the daggers where they need to be here. So we can arrange this so that these LKs all have trace 0. And when we design, at the end of the day, we're going to be designing algorithms, okay? LK. Did I get, okay. All right. I wish I could change it in real time, but okay. Dagger goes over here. So when we design these operators, we're going to design operators that sort of take us to, that change the state, and they're going to have at the end, they're going to have a projector that conditions on acceptance. And then this term here is just sort of a necessary term to ensure that it's a trace preserving map that we get, okay? And that will sort of represent the reject case. But really, when we're designing the operators, we're really thinking about sort of designing things so that it accepts with the right weight. For what I will talk about here, we will never need to use the coherent part. It does come into play in later papers, though. So for our purposes here. So what we want to do is now design these things and simulate them in the same way that there are algorithms to simulate Hamiltonian evolution. Okay. Okay, so how do I tell you about what the L's are? So if we have an algorithm, I have to deliver the description of the Lindbladian in order for an algorithm to actually simulate it. So how do we specify this? Well, here's one way to do it, and it's called a block encoding. Okay, so this is going to be the description of the L operators. So I have some input to my circuit, bunch of ancillary zeros set to 0, and there's some unitary operator that operates on all of the qubits. The output will be here, and the operators will condition on the last register being 0. Okay, so this is part of the operators. And then the remaining bits are the index for the operators. So, and then what we get up here is just the output of LJ. So quantum circuit, projector at the end, projecting onto something, and then the remaining bits tell us exactly the index of the operator. So this whole circuit gives us LJ tensor projecting onto J. Okay? Given a block encoding, there are algorithms to simulate this dynamics. Okay? I think the first one is Cleveland-Wang, but I don't know. That's the first one I'm aware of. And then it's been sort of improved upon since then. So what I'm going to do here is describe the simplest possible one, not the most efficient, okay? Because it'll be sort of helpful just to see how that works. So let's say I have a block encoding, okay? What I'm going to do is introduce a very weak measurement that tests, is this last register 0? So I'd like to project onto it, but I don't know how to back up if I can't. So I'm going to do a weak measurement here. So this just, if it happens to be 0, we rotate a qubit slightly, okay? And then a 1 in this case, if this qubit is 1, that represents sort of an accept case. And 0 represents reject. Okay, so in the 0 case, I want to invert everything. And then I'm going to trace out all the bits, the qubits, discard, and continue. So this is one iteration of an implementation of the Lindbladian. And if you kind of work out what the circuit does, it's approximately I plus tau now times the Lindbladian. Okay, plus some error terms that scale with tau squared, which is approximately e to the tau L. Okay, so can I answer questions about this? All right. And it's not as efficient as other implementations because we have a slowdown introduced by the weak measurement. So if the mixing time, if I'd like to simulate my Lindbladian for some time t mix, the number of steps, I'm going to have to introduce 1 over tau extra steps in order to achieve that. The total error per step, it's tau squared. So the total error is t mix times tau. So I need this to be small. So my tau has to be bounded by 1 over the mixing time, and I get the mixing time is therefore at least t mix squared. There are better, fancier implementations that go linear in the mixing time. Okay? All right. Yeah.
So for this slowdown, is there any like physical meaning? Or it's just comes from this error analysis?
I think it just comes from the fact that you're weakly measuring and that you're only moving ahead in your Lindbladian with a small likelihood. And the weak measurement means that you're not tampering with your state too much. So because it's the weak measurement, think of it like implementing Metropolis, but you accept with probability tau instead of the regular. You have a slowdown of a tau introduced inherently into your process.
So it's related with the fact that I cannot choose a larger step size. Like,
Yeah. It's related to, I mean, the way I think of it is for every time scale t, you have to do 1 over tau extra steps in order to get to the same place.
How exactly are you defining t mix?
That's a good question. So I think there's a sort of a standard time scale encoded into that. You could also think of sort of a discrete time version of this quantum metropolis, which we don't know how to implement, but then there would be a sort of a well-defined discrete t mixing time. But I think inherent in this Lindbladian that we'd like to simulate, there is a mixing time which is related to the spectral gap of that thing. So there is a continuous notion of mixing time in that Lindbladian which is related to that spectral gap. I don't know exactly how it's related to the discrete time version. Okay, so
just to complete it is so what? How efficient does this get? You said this was just area.
Yes, there are versions that scale linearly with t-mix. And other error parameters, which I am sort of sweeping under the rug. What's the best? Andras will know.
I think it's t log t over epsilon t mix log t mix over epsilon.
All right, so, yeah.
So what makes more sophisticated implementations? Is it not a weak measurement based one?
You don't measure after every step. Andras is gonna sort of pick up where I leave off and we'll probably describe some of those. Yes? Maybe not?
There is a talk about simulations.
There's a talk about simulation later on, so, yeah. Okay, so any algorithm that sort of prepares a Gibbs state at some point has to do some measuring of energies. It's not necessarily in the form of a black box quantum phase estimation. In the CGKB algorithm, the pieces are there, although not sort of encapsulated as a quantum phase. So I'm going to do a little bit of review here of quantum phase estimation. We have some unitary operator, and this is its eigenvalue. And what we want to do is calculate what this phi is. Okay, so this is one of the oldest standard algorithms from quantum algorithms. We start out with our eigenstate and a register. We prepare an even superposition of all of the times in the register. Then a controlled application of the unitary. So each unitary is applied t times. And what happens then is we pick up a phase that's proportional to t. It's proportional to phi and proportional to t up there. And then QFT sort of gives us an approximation of what this phi is, scaled by r. So r is 2 to the r. Okay, so we get some approximation of this number. So QFT, think of it as sort of translating this phase into this register with some error. Okay, let's talk. So in general, we're going to be using our exponential of the Hamiltonian here, and that will allow us to sort of estimate the energies accordingly. I'm going to talk about phase estimation just in the context of a generic unitary, but there's a translation if you're using this particular unitary between the energies and the phi. So it's just a constant factor. All right, so what does it mean to get an estimate? What it means is that we're getting some superposition over different values, which we hoped is peaked at the true value. Okay? Now, if it just so happens that the true value sits and is perfectly described by an integer over r, then we have no error, and we get exactly one output. But that usually doesn't happen. Usually phi is sitting, so the number of the set of things that we can represent are integers divided by r. So those are in my finite precision register. That's all I can represent. And usually phi is going to be sitting in between those two values. So we get the output is some superposition of outputs that is peaked around the true value. Okay? Now there are two things that are unavoidable. One is the precision. Can't ever be better than 1 over poly because our running time depends on that precision. Okay? Another thing that you can never get away from is that there's always some inherent non-determinism. We can't deterministically take the floor or the ceiling of this thing. Okay? We can't deterministically round to one direction or the other. So that's inherently deterministic. But what you can do is improve the bounds of this tail. Okay? So if you just use the regular vanilla variety quantum phase estimation, these tails tend to be heavy, meaning that if I'm looking for an error that scales, so R, remember, is like a polynomial. Okay, so if I'm looking to actually look at the likelihood that I should have 1 over a polynomial, that's going to be roughly equal to 1 over a polynomial. So it's inherent that I'm going to have these heavy tails that are 1 over a polynomial. In the analysis, I'm not talking about proofs much, but just in the analysis, at the end of the day, this is not sufficiently accurate. And when you think about why that might be the case is, let's say I'm looking at my Lindbladian, and I'd like to say if I plug in the Gibbs state, it should be 0 exactly, because the derivative should be 0 right at the Gibbs state, ideally. Approximately, I'd like it to be close to 0. But this is a huge matrix. It's like an exponentially sized matrix. And I've got two sources of error. One is that I'm off by a little bit, and the other is that I'm off by, that phase estimation is way off. In order to control that second error, I'd like to be able to say that the contribution in that matrix, that very large matrix, entry-wise is exponentially small, in order to be able, because there's an exponential number of entries in that matrix. So we really need this to bound the tails of this to be exponentially small. There are two ways to do this. The original one, introduced in Nielsen and Chang, takes a bunch of runs, independent runs of QPE, and then takes the median. Okay? And this is very accurate. With high probability, you're getting one of the two best estimates, and the tail is exponentially small. It's a little expensive, though, because you have to have now multiply the number of qubits in your register by a polynomial. Okay? There's an alternative way to do that, which prepares something other than the uniform superposition. Okay? The first reference I'm aware of is in this paper in which they use a Kaiser filter. I think this is kind of well studied in signal processing. There's been a recent paper that actually optimizes the filter that they've used to actually optimize the probability of error. Anthony and Andras and company use a Gaussian filter. Okay, this has a particularly, so what we're doing here now is instead of preparing an equal superposition, we're preparing a peaked Gaussian and running then QPE on that. And just to give a little idea of why that works, so we prepare the Gaussian, then the other two steps are the same. And the reason that I guess I didn't have this on the slide. Yes, here it is. So the reason that this is helpful is that if I apply the quantum Fourier transform to a Gaussian, I get out a Gaussian. So if I pick this sigma nicely, I start out with something that's really peaked, and I output something that's also really peaked. So I prepare this Gaussian state, then the same sort of controlled application of the unitary. So now I have these Gaussian terms which are peaking at a particular point, and I still have this phase term here. And then we do quantum Fourier transform. And what this does is it outputs a Gaussian, and this phi shifts it. So in the end, what we get is sort of a shifted Gaussian, which is also nicely peaked. Okay, so this improves the probability of error dramatically, and you don't have to do multiple runs of quantum phase estimation. You just have the added overhead of preparing this Gaussian state. Okay? Okay, so we are ready now. I'm going to step through a couple possible Lindbladians for, yes?
What is the speed up by this?
The cost of preparing the Gaussian?
By this boosting strategy.
It's just an additional cost here, and I think it's polynomial in R, certainly. Do you know the complexity of?
Preparing the state?
Yeah.
Yeah, it's something R log 1 over R2. Yeah.
It's polynomial in big R, which is the number of qubits. So it's polynomial. Is it a polynomial in the register, in the number of qubits in the register? Yeah, number of qubits. So it's actually logarithmic. Okay, so here's.
Sandy,
yeah.
Before you present this different Lindblad simulation algorithm, just want to say the ideal thing, the setup is 45 minutes plus 15
Oh.
people to ask questions.
Okay.
Yeah, of course it's not.
Okay. We started at 10 after, so just a few more minutes. All right.
Yeah,
All right.
so,
Okay, so I will step through two possible Metropolis-like Lindbladians. This one is sort of a Frankenstein. It's sort of taking bits and pieces from other algorithms. So we'll select a jump operator. I'm going to start in some state, apply QPE, and have some estimate of its energy. Tweak the state, apply my jump operator. Now I have some superposition of places I'm going to. Apply QPE again, but now put the result in the second register. So now I have an estimate of the first energy and an estimate of the second energy sitting in those registers. And I'm in a position now where I can now calculate the probability of going forward. So given that, we can calculate this probability that we'd like to accept, and we're going to then rotate a qubit slightly according to this probability. So in the end, this is the probability. If I were to measure it and get a 1, then I want to accept and go forward. And by the way, this is That's the operator. This is the original algorithm from 10 years ago by Christian Tem and Frank Verstraete et al. What they did is they just measured it outright. Except you'd like to go forward, and backing up, they used the Marius-Watrous procedure to try and back forward. It's really complicated and problematic, especially in the presence of error. There seem to be some issues with the analysis, and I don't know if there's a Marius-Watrous based algorithm that will work, so it's not clear. But this is what that original algorithm did. But you could take this, this has to be some form of boosted QPE, whether it's median or Gaussian. But you could take this and use it to define Lindbladians, okay? Where this now, the operators are conditioning on accept. And these are the tags of your Lindbladian operators. And so you could then put weak measurement on top of it, conditioned on accept, rotate a qubit by tau, and otherwise the identity. Invert if it's 0, trace everything out and refresh. So this is a possible, I actually haven't done the analysis of this one end to end. I started with this one because it's, I think, a little bit more intuitive. But now let's mix it up, and now I'm going to step through the CGKB Lindbladian from step to step, and we'll see the algorithm from end to end using the weak measurement. Okay? So we're going to start with the Gaussian state here, okay, to boost our likelihood. And now what I want to do is apply the controlled time-evolved operator, okay? Some people live and breathe in this world. I don't, so we're going to spell it out very exactly. Okay, so first what we do is we a controlled inverse Hamiltonian, and I pick up minus the energy. There's a constant factor in there to make it between 0 and 1. Okay? And these are my Gaussian weighting factors. Okay? Then I apply the jump operator and tweak the state in some way, and I get some superposition of new places that I might go to. Okay? Then we apply the Hamiltonian operator in the forward direction. But now, since we have the new state here, we're evolving according to the new state, and we end up with a plus EK here. So at this point in the phase, I have the difference that I'd like. And at the end of the day, the probabilities of accepting or rejecting depend on this difference, not on the actual energy. So I've directly computed the difference. They've directly computed the difference instead of individually computing EJ and EK. Now we have our nice Gaussian weighting function to boost our accuracy. But when I apply QFT to this thing, now this difference is going to get translated into this register instead of the individual energies. Okay? So when I apply QFT, I get some approximation of the energy difference instead of the energies themselves. Okay? And then, same thing, now we have enough information with this energy difference to now rotate, so we can rotate a qubit with the probability of acceptance, okay? Because there's enough, it depends only on the energy difference, not on the individual energies. Now, this is a valid set of Lindbladians. We're conditioning on acceptance. The label now is, instead of the energies themselves, it's the difference in the energies. And we get some set of operators. This should say delta E there. And to this, you can then now apply the weak measurement. So now you can sort of take this qubit and measure it weakly and invert everything if it's 0 and trace everything out. So end to end, this is the algorithm using this very simple weak measurement implementation. Okay. Questions? So Jiaqing and I came across this. We read the Lindbladian-based paper, and we thought, well, is there something that's closer to the Metropolis, the spirit of the Metropolis algorithm? So our algorithm is very similar to that first one that I showed you, the one that actually computes the energies directly. We didn't use the weak measurement. We used a slightly different mechanism. So here's the QPE, jump operator, QPE. We end up with these two energies sitting there. Same W, but instead of doing this two-step where you measure the probability of acceptance, put that in a qubit, and then use another qubit to measure weakly, we did both in one step. So this actually rotates according to tau times gamma. And then there's sort of two steps to acceptance. We measure accept as 1. 0 we'd like to rewind, but we can't directly. And so we just implement the inverse of W this time, just this operator, measure again. And 0 is a reject, and 1 again is an alternate accept. And so what we proved is that these two outcomes are actually very close with an error of tau squared. And this rejection operator gets us back again with an error of tau squared. So it's similar to the weak measurement implementation, but slightly different. So we've gone end to end 3 different algorithms, and I think I will end there. So.
Thank you, Sandy, for the great talk. Also, it's great for setting the stage for the week. Now, any questions from the audience?
I'm going to deflect all the questions to Andras probably, but anyway.
So back to last time, so we're confused about whether this is a implementation of the same Lindbladian or it's actually also different Lindbladian.
I think it's the same Lindbladian. It's a different implementation of it, but I don't know that it's a generic Lindbladian implementation because it seems to depend on the structure that you've got some kind of acceptance rejection embedded in your Lindbladian. So I don't know if there's sort of an alternate generic weak Lindbladian implementation here or not. I don't, because we do this sort of partial backing up, and I don't know that there's an analog in every single set of Lindbladians that you would have. So it seems to be a little bit unique to this particular setup.
Yeah, I can give some explanation.
Okay, good.
So like I think it's conceptually related to Davis generator. After using in more details, but it's technically slightly different in the sense that so like in the previous work 10 years ago, like in the Christian's paper, so to make this statistical balance, you somehow need some kinds of shift invariance. So the Davis generator achieved the shift invariance by only computing the difference between energies. So it never write down the two energies. So that somehow achieves shift invariance. So here we did write down the two energies. We achieve shift invariance by we achieve shift invariance by using a QPE and a variance of QPE random. It's something like this. So it's like conceptually they are similar, like they're technically slightly different.
Another question back there.
I'm curious about the status of this algorithm because I've heard a lot of mumbling about problems, but is it wrong or does it work? And then if it works, maybe what's the motivation for doing something else?
So I don't know, honestly. I've spent some time reading the paper, and so the original sort of description of the problem was the fact when you're bouncing back and forth, implementing variate watches, you may not end up with zeros in your register, so you need a version of QPE that can take in non-zeros, and when it computes an estimate of your phase, it sort of adds it in, and this is what is called shift invariance. So you get a sort of a rotated version. They assume shift invariance. they also assume boosted in very tight, like the likelihood that you're off by even those two closest approximations is essentially 0. And there's evidence that shifted and boost invariance together cannot be achieved. So one can be achieved.
In what sense?
There's a proof in deep in the appendices of the original paper showing that, but that's a very strong negative proof. It says that you can't have 0 error. So I don't know if that aspect of it is fixable. There are other places in the paper where there are jumps made that I also can't fix. So I don't know if it's
So it's not verified, is that?
Yeah, I don't know.
I would say that the algorithm that they write down is like there is no such algorithm by topological abstractions, and then whether some variant of this algorithm works, it's unknown, but it's certainly not proven in the paper because those variants are not even in the paper. So some variant of it certainly works because you can view all three algorithms as a variant of that algorithm, and then some of them has proofs. So some variant works, the variant which is there doesn't, and there is some gap.
But the essential question is there sort of a version that relies on Marriott-Watrous to do the rejection? That I really don't know the answer to.
And the point is all recent simulation algorithms, none of them is Marriott-Watrous.
Yeah.
And what would be the advantage of using Marriott-Watrous? Would there be an advantage, or is it just?
We set out just to have something conceptually simpler to the original and closer to the original discrete-time Marriott-Watrous algorithm. So maybe there's stuff in the literature for the discrete-time walks that could help bound mixing times. Maybe there's more intuition around that. I don't know.
Sorry, you're asking what's the advantage of Marriott-Watrous?
Yeah, if there's an advantage.
So like, I think it might be faster because like, so I mean, it depends on how many, how many times you need to repeat for the Marriott-Watrous one. But it seems like inherent in discrete time. So I mean, for the Lindbladian, okay, so first I have no rigorous evidence to prove it's faster. It seems like for Lindbladian simulation or for like component evolution, even if you use a more advanced method, there will always be some. So like you need something to distinguish the energy space, energy is different, something like this. So you need to do something. I mean, there will be some overhead of simulation string. So that's a hope, like the discrete time chain will be faster because it's a different mechanism. Yeah.
I think it's likely to be faster than the weak measurement versions. I don't know that it's going to be faster than the fancier Lindbladian simulations, though.
Yeah.
Because in the weak measurement, you've built in the slowdown. It's just it's always there. Whereas in the Marriott-Watrous, chances are you're going to back up faster. It's a really worst case sort of analysis that you have that you can spend that much time trying to back up.
So speaking of which is faster, what's the complexity of this version of the algorithm?
I think it's similar. We used sort of the median finding boosted QPE, and so there is a blow up in sort of the number of qubits. And then otherwise, I think it's going to be very similar to the weak measurement-based running time.
So it would be T-mix square, and the idea is that using Marriott-Watrous, you get T-mix.
Yeah, there could potentially be a polynomial slowdown in the number of times you have to try to get back, but that's a pretty pessimistic analysis. So, but worst case, yes. Yeah.
Can I have a further remark? Sure. So I think we have a further motivation of why we want a discrete time chain instead of a continuous time chain. Okay, I think both of them are very good. So like just to give some more motivation is like I think there are a lot of variants of Metropolis algorithm in the classical world. Like they're not the standard version, but they're also correct. for example, there's something like reject sampling. Delayed rejection is like if you get a rejection, instead of like revert back to the original state, you propose a new jump. So I mean, there are many variants of Metropolis algorithm in the classical world. So we hope like discrete time, like Metropolis quantum Gibbs sampler. If you have something like this, you can adapt the classical techniques to the quantum world. So that's a hope. That's a potential advantage. Yeah.
Okay, one last question. Yeah. Can you say something about the complexity of encoding the Lindbladian block encoding? And does that depend on the Hamiltonian?
It does, because you have to do the evolution, e to the IH. So that's going to be Hamiltonian dependent. So that's going to depend on the complexity of implementing that. So in that sense, it does depend on it. So we have the steps you have is, phase estimation, and then the Hamiltonian, simulation. And probably the simulation will dominate that, because you're going, sort of simulating that over a polynomial time scale. So, and it depends very much on the Hamiltonian then, because there's a lot of work in sort of implementing those. 2D, it might be faster than if it's some arbitrary connectivity.
What about the block encoding itself? With the jump operators?
The jump operators, I don't think are problematic.
They can be sparse?
I think, like a jump operator would be pick a random single qubit Pauli and apply that. So those are generally very simple. You just need that the algebra generated by those jump operators are sort of generate the space of unitary operations. But, analogous to flip a random bit in the classical case, you're picking a random Pauli or random qubit and just tweaking that. So that part is quite simple, potentially. I think most of the complexity is in simulating the Hamiltonian.
Maybe let's thank Sandy.